All right, it's been 5 minutes. I'm not seeing anybody in here. So I'm just going to go ahead and start. And the reason why I'm going to start is because hopefully somebody will show up other than just me. So what we're going to do is we're going to share my screen and quickly hop over here and launch this. All right. I'm going to wait just a couple more minutes and then we will start. So the question that you've come here to learn about is about the ARIMA model. So let's just briefly talk about what is going on with the ARIMA model. In particular, what we care about with the ARIMA model is that it is a time series model, which is a form of regression, and that is the form of which is just a statistical model. And so ARIMA models are just built on top of all this machinery. You can sort of think of it as the top of a pyramid. It's the peak of the pyramid. It's really what we need to do in order to get to the very top of that pyramid is to learn about statistics and regression. And then we're capable of talking about time series. Now, time series is kind of interesting because unlike other forms of regression or statistics, there is a natural ordering to the data. And the reason why that's important is because that natural ordering of the data, it gets you something that you just can't get anywhere else. You end up getting weird correlations between the past and the present and even the future. All of those things are possible in a time series, whereas with the vanilla type regression, my answers to a survey are completely independent of your answers to a survey. And so with regression and statistics, we generally don't see this time dependency. But the problem is that time moves forward at a constant pace. And because it moves forward at a constant pace, it becomes a really natural way to collect data. And so time series is probably one of the most important types of data that we can analyze just because it's so common. And so what we really need is we need good models that satisfy all of the assumptions of a regression, but we have to add other machinery to those models to create the way that those models actually happen. And that's where ARIMA comes in. ARIMA stands for an autoregressive integrated moving average. That's the full technical name of the model. And ARIMA is exactly that. It's a full model so let's break that apart really quick. Autoregressive, that means that we have these weird correlations across time, right? The past affects the present, essentially. Integrated means that we have a model that's non-stationary. It's moving through time. And the moving average bit, it also captures something about how the model is changing over time. So why would we care about forecasting at all? And the reason that we care about forecasting is well, why do we care about time series? It's forecasting, right? That's what you get when you get talking to me live. I'm going to make a couple of mistakes here or there, but time series, we care about it because we care about getting answers about what the future is going to look like. And the thing is that forecasting is hard. Now, what you can see from this picture right here is that I sort of start at this point, but then we have all of these diverging paths. And I like this little graphic for that reason, is that we don't really know what the future is going to hold. So what we care about doing is sort of finding the average path that our model can take. And then sort of what is the worst case and the best case scenarios that our models can take. And then we want to know, how confident are we 95% of the time that we're going to be within some sort of band, that sort of thing. That's what we really care about with time series. And doing that is actually really, really, really hard. The reason why it's hard is because we have this problem where we don't know what the future looks like. So what is the general idea with forecasting? The general idea is that we're just going to draw a line through our data, and then we're going to extrapolate that. That is a completely valid way to forecast using time series. You just draw a line through your data, and you just keep extending that line onto the future. The problem is that, like I said, the past changes what we see in the future or the present. And because of that, if I have a small little wiggle in my lines somewhere in the past, it could change dramatically whether I move that wiggle just a little bit further into the future, a little bit in the past. It can change the path that my time series is going to take, regardless of what's happened, right? My path will diverge. Which is why just drawing a straight line through your data, that's generally not a great way to approach time series at all, and there are a couple of reasons for that. And one of the big reasons is that you violate all kinds of assumptions with your data. And we'll see that in just a little bit. But those violations in the assumptions that you make in that regression model, they end up compounding more and more and more over time. And because of that, your forecast gets worse and worse and worse over time. And so you basically can't say anything at all if you do this. And that's where the ARIMA model comes in, because the ARIMA model, it lets you do those sort of things. It lets you account for those minor discrepancies in the data. All right. So this is an example of what I'm talking about. On the left-hand side is me just drawing a straight line through the data and then extrapolating that line forward. That would be this yellow line right here, or orange line. And what you can see is that, yeah, it would do a pretty decent job of predicting what the data set is going to do, that orange line. But my confidence in where that orange line is, you can see that it's going all the way from -400 to +400. And actually, this is a time series that I've been looking at recently. And what it's a time series of is wait times. And so a negative number actually doesn't make any sense at all. And so, basically a straight line through my data, it's just a garbage forecast. It doesn't do anything. Now, on your right, what you'll see is a very silly, I'm just going to hide that. It's just a really silly ARIMA model. Basically, I just took an ARIMA model. I did order 1, 1, 1. I didn't check whether that was a good or a bad model. I just did an ARIMA model and added, an AR term. I did some differencing, and I did an MA, and then I forecasted that forward. And what I'd like to point out is that these two models right here, I have the exact same forecasting horizon for each of those models. And because I have the same forecasting horizon for each of those models, that orange line is actually the same length. It's kind of hard to tell that it's the same length, that I'm actually forecasting the exact same amount of time steps, because of how squished that first graph on the left is, because of that giant confidence interval in my forecast. But what you see with the ARIMA model is that my confidence interval for that forecast, that's actually pretty darn reasonable when you just look at, just eyeballing that. That is a really reasonable forecast window, or a forecast confidence interval, right? Basically, I'm saying my forecast is this orange line, but I think that it could be anywhere between these gray bars, right? And just looking at this one, my forecast, I can't really say where it's going to be. But in this one, I'm just eyeballing that, right? Like this blue peak right here is almost to the top of this gray line right here, which just sort of says, yeah, I'm actually doing a pretty decent job of forecasting. The orange line is my best guess, but I could be anywhere between there, and those seem actually pretty darn reasonable to me. And that's without actually going through any of the steps to figure out how to do an ARIMA model. All right, so let's talk about what the major assumption of regression is. And it's an assumption that doesn't get talked about a whole bunch in like a freshman statistics class in college. It's an assumption that, if you take econometrics, that they sort of gloss over. But it is an important assumption that they're making. And the assumption is that the errors that my model is going to produce are going to be normally distributed, and then I'm going to have a constant mean and I'm going to have a constant variance. The problem with that is that if my past informs what my future or my present observations are going to be, my mean by necessity is not going to be a constant number, because if I'm just keep stacking those things on top of each other, I'm going to wander around. I'm going to go way up. I may still have a zero mean overall, but my zero mean is not going to be one right after the other. If I have a positive number, I'm going to keep getting positive numbers. I may turn around and I might start getting negative numbers, but I'm going to have like my distribution is going to be more lumpy than a normal distribution should be. Also, importantly, the ARIMA model does assume that you're going to have constant variance, but that's not necessarily going to be true with time series data, which is where like your ARCH models and your GARCH models come in, because those will actually model non-constant variance. So just going back to that other model that I was showing you, this is what our errors look like for right here for a straight line model on that data that I was showing you. What you can see is that it actually is centered around 0, which is good. But what you can see almost immediately, if I go back, right, those tails die off really quickly. I'm essentially at 0, at -3, and +3. Now, if I go forward here, I don't hit 0 until -50 and +50. Plus, this distribution, it jumps really, really, really tall, really, really quickly. And so what we call this in statistics language is that this model has excess kurtosis. And all that kurtosis really measures is how pointed my data is, right? How pointed is the peak of that data. And if it's too pointy, then we say that it has excess kurtosis. But fortunately, like my data, it's running from -50 to +50. It looks like my variance is probably okay. So I should be good to go with an ARIMA model versus a GARCH model or something like that. I don't see too much difference in my variance. But the big problem that I'm seeing is how steep and pointy my model is for a straight line model. And so what we're going to do is, and what you saw with those forecasts a couple slides back, is that an ARIMA model will sort of fix the problems with this model, and it's going to cause that model to have less of a peak, because we're going to account for some of the things that are causing it to be so peaky, right? Or that cause it to have excess kurtosis, right? So the big problem that's causing it to have excess kurtosis is that the model is not stationary. And so how do we get rid of how do we get a data set to become stationary? It's actually kind of easy, because all we have to do is take differences with the lag of the current observation with the lag, and that usually gets rid of your non-stationarity stuff. Now, there are ways to test whether you have non-stationarity. The augmented Dickey-Fuller test is the one that I tend to use personally, and it's the one that I would recommend using. But it is one of those things. There are multiple tests that exist. Augmented Dickey-Fuller is probably the most common, but you do have to make sure that you are going to manage its assumptions correctly. But differencing the data is the key idea behind the ARIMA model. Once you figure out that you do need to do that, it becomes the most important defining characteristic of the ARIMA model. It's actually a great idea to do it, because basically when you assume that your model is wandering or that it has a trend, you basically differencing it says, okay, I don't care about what the level is, I just care about how fast is it growing over time. And by differencing that, I should have about the same amount of growth per period of time. So by doing that difference, what you're going to end up doing is you're going to end up having a constant model. And so I'm not wandering across time. And that's really what the ARIMA model does, is it's basically trying to force the model into a random, you're basically trying to reduce your model down to just random noise. And once you have it reduced down to random noise, it becomes really, really easy to forecast that, because you just say, this is what my random noise looks like. Let's just take it a step forward in time, add in some random noise, and then propagate through the model. right? That's basically what an ARIMA model does. But the problem is that differencing the data, you can actually still have signal in the data, right? There are a couple of things that you could end up doing, right? So let's assume that your data is trending, but at an increasing rate, right? So if it's increasing at an increasing rate, if you difference it again, that should, as long as the increasing rate is constant, you should be able to see in your data that that differencing it twice will get you down to stationarity. But what if you have half a step in your differencing? Well, that creates a little bit of a problem, right? And I love this this little advertisement. I'm not sure where it was. I just found it. But basically, it's actually very, very applicable for ARIMA models, right? If you're not down to random noise, if you're still picking up some sort of signal, you haven't gone far enough in differencing yet. And that's where the AR terms in your ARIMA model come from. They come from the fact that you haven't gone far enough, that you're not going to take a full step towards differencing, but you're going to take a partial step. So let's take a look at the math. And other than this slide, I only have one more slide that has math in it, so don't get too scared. AR is a partial difference. And the reason why I wrote this out is so that I can show you that it is a partial differencing. So this is what an AR model looks like. YT equals beta naught plus beta 1 times the lag of Y plus some error term. That's what an AR term looks like, right? That's what an AR1 regression looks like. Now, what we expect is that this beta 1 coefficient right here, that beta 1 coefficient is going to be between -1 and 1. And so that's what we would expect it to be. Because we expect it to be between -1 and 1, we know that that is some sort of partial step towards a full differencing, right? It's a partial difference, right? And you can see that right here in the second equation that I've written. Just by moving the beta 1 Y lag over to the other side by subtracting it from both sides, what we end up with is YT minus a partial difference of the previous value is equal to some constant and some error noise, right? And that's exactly what we want to do with an ARIMA model. We want to get the model down to a constant and some noise. All right. Now, what if you difference it, you take an AR term and you difference that, and you've gone too far? What if I told you you've gone too far, right? And I chose this particular meme for this slide for a very particular reason, and that's because we are definitely going to go down the rabbit hole with some math. And I promise you this is the worst math that I'm going to do in this presentation. And here it is. I know this is a lot, but let's just go through it step by step. We're going to add a little bit back in. And the way that we're going to do that is this is the equation for an MA1 model, where YT is equal to a constant plus a little bit of the last period's noise plus this period's noise. So the noise for last period can be defined as the predicted value of our lag minus our actual value of the lag, and we're going to multiply that beta 1 through. That's how we get to this guy, right? Now what we're going to do is we're going to take this beta 1 yt minus 1 and we're going to move it over to the other side. We end up with yt plus beta 1 times the lag of yt, right, is equal to a constant plus beta 1 times the predicted value of yt minus 1 plus our error term. Okay, that we haven't gotten down to constant plus noise yet, but what I like to point out right here is that we can actually stick this back into our model and then iterate recursively through that. I'm not going to beat your head with that math. I'm just going to go to the next step, because eventually what's going to happen is that I'm going to get beta 1 times beta naught plus beta 1 yt minus 2 minus beta 1 blah, 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 right? And so that's where this step comes from. That's how you get from here. You just keep doing this step over and over, and this step over and over and over again until you run out of data. If you do that long enough, because beta 1 is going to be between -1 and 1, beta 1 is going to continue shrinking and shrinking and shrinking until it gets to 0. And when you hit that, then it doesn't matter what my former yt values are at some practical limit point. That's going to be, that multiplication is going to end up being 0, and you end up with this thing right here, right? You get yt plus the sum of beta 1 raised to the n times yt minus n, whatever, right? You get a big long string of those. So what you're doing, what I want to point out with this one right here, is that I've got yt and I'm adding a little bit of every single other y back to it. All right. And because I've gotten every single, I've added just a little bit back to every little thing, right? And then over here on the other side, what you end up with is you can factor the beta naught out, which is kind of cool. And then you just end up with the sum of beta naught times the sum of your bi's rate, your beta 1's raised to the i's power. I know this seems really, really complicated, but the nice thing is that beta naught times the sum of these beta 1 terms, actually beta naught and beta 1 are just constants. So beta naught times the sum of this infinite sum right here is just a constant, which we're going to call theta. And so we end up with yt plus blah, 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 blah equals constant plus noise. So that's how your MA model gets you back to there. So the main point that I want to make from this slide is that the AR is just a difference and the MA is just adding a little bit back. The whole point is to get to constant plus noise, which would imply that you have a stationary model. So what is ARIMA? The goal of ARIMA is to model your data as some sort of random walk, a constant plus some noise. And you difference it to make it stationary. You do a partial difference if you're not quite to stationarity yet, and you add a little bit back with an MA term if you take a step a little bit too far, so that basically all that you're left with is some noise, and that's it. And that's what the ARIMA model is. So if you take nothing else from this presentation, it is that your ARIMA model is just modeling random noise. That's it, right? The difference will get rid of the constant, and so That's what this difference does right here. The I gets rid of that constant, and so all you're doing is modeling random noise. That's what you're trying to get to a point where all you have left is a normally distributed random noise model. That's it. That's all that ARIMA models are. All right. So let's talk about how you practically decide on the order. How do you decide how many AR terms you need, how many MA terms you need? And so what we're going to talk about is the PACF plot, the ACF plot. That's the partial, let me just define those really quick. That's the partial autocorrelation function plot and the autocorrelation function plot. And then we have information criteria. Now I want to get to some practical examples before we end at 11:30. Now I've only got about 20 minutes left, so we're going to go through this pretty quick. This is what your ACF and PACF plots look like. At the top, I have the ACF function. At the bottom, I have the PACF function. Now, you use your partial autocorrelation function to tell you how many AR terms to look for. If you see this sort of signature in your ACF, PACF plot, what I would say is immediately this looks like you have an AR term, at least one AR term. So I've got this guy right here, so AR1, so this is AR0, AR1, and then AR2, not so bad, AR3, not so bad, AR4, not great, but probably within an acceptable level, probably. 5, 6, and 7 are getting really dangerous because of this one right here. It's probably number 7. I'll probably have an AR1 and an AR7 term in here. Typically, what you do is you'd use a seasonal ARIMA model to model this, where you'd have an AR term, and then you'd have an AR1 term, and then an AR1 seasonal term, with the season being 7, right? The partial autocorrelation plot, if you see something that looks like this, that would mean that you have an AR1. You have an AR model, right? Now, the signature for an MA model is just the exact opposite, right? Where you have, this is what a signature for an MA model would look like. You have a bunch of non-significant MA autocorrelations, and you have a bunch of significant, you have one, and you can sort of see some seasonality in there, right? And this one doesn't look great, but there may be an AR term that's needed based off of this, but this signature right here really tells me that we need an MA function. And so just keep that in mind. Use your ACF plot to tell you how many MA orders that you need, and the partial autocorrelation function to tell you how many AR terms that you need. Now, the information criteria selection is kind of an interesting thing. Basically, what you do is you just try a bunch of different models, you calculate the information criteria for each of those models, and then you just pick the one with the lowest information criteria, which would be the model that gives you the best fit. And information criteria, it's just the log likelihood. You do some transformations on it, you add a penalty for how many extra terms you're estimating, and that's all that the information criteria really is. So it really is measuring how good your model fits while trading off complexity for your model. Like I said, it's just a transformation for the log likelihood. You're adding a penalty for those extra parameters. It comes in two different flavors. A Kaiki information criteria. I went through graduate school and I never learned whether or not I was pronouncing that correctly. I believe I am. He is Japanese, but everybody just abbreviated AIC, and that's probably what you would see. And then there's the Bayes information criteria, which uses ideas from Bayesian statistics. You have a prior for what your likelihood should look like. And that's really the difference. Is AIC is more of a frequentist approach, and Bayes is obviously a Bayesian approach to modeling the information criteria. And then you can actually calculate how good a model is relative to another model, by comparing those two, by comparing the AIC from model A to the AIC in model B, you can actually get how good they are relative to each other, which is good. Anyway, that's the end of that. So I'm actually going to come over here and stop sharing my screen. All right, cool. And let me go over to YouTube and see if anybody has any questions. I don't see any other questions right now. So what I'm going to do is I'm actually going to come over here and we're going to share my screen again. And this time I'm going to go over some code with you guys really quick. Yeah. So this is actually the data that I was using in the presentation. I wanted to go over this really quickly in the next 15 minutes or so. So I'm just loading some data. Here's what it looks like. And then we've got, I'm making sure that my pandas index is a date time, and I'm extracting the hour, and I'm grabbing just a couple of hours from each day and calculating the mean value, and that's giving me a data set that looks something like this, where I have days and values, right? We can plot what that looks like, and that's what it looks like. The other, right, our histogram. Now, I always like looking at the histogram because it tells me a little bit about how the data is distributed. Just like a, so I always plot two, right? I plot the kernel density estimator, and then I look at the histogram of the data, because sometimes I get more information by looking at a single line, and sometimes I get more information by looking at what it looks like when it's binned. Okay, that's fun. Let's look at the autocorrelation plot. And looking at the autocorrelation and partial autocorrelation plot for my time series, I can definitely see that there is going to be a strong AR component, AR1, possibly an AR6 or 7 component to this model, which is fine. Then I'm going to compute my augmented Dickey-Fuller test, and I got a negative 4.68, which has this p-value, which is highly significant. Now, the null hypothesis on an augmented Dickey-Fuller test is that my series is not stationary. Therefore, this model rejects that null hypothesis, and I conclude that my data is pretty stationary. which we can look at. I believe it's TS, right? I already have it, yeah. So ts.plot, and we'll just take a look at that data. Yeah, okay, there might be a little bit of a trend there, but it's not great. It looks pretty stationary, actually, but that's fine. So just looking at this right here, I'm thinking an AR1 through an AR7 model might do the trick. It would be a pretty simple model, although just looking at that, I already went through and I calculated that. So we do this, we run our ARIMA model, we look at the coefficients, and I've got my constant, my AR term, which looks about right? 0.67, looking back at the partial autocorrelation plot, it's pretty close to 0.7, so that makes sense. So very, very significant, right? My Z value or my T value is a 35.7, so very, very significant. But let's take a look at the residuals. Yeah, that actually does look pretty darn stationary to me. We may have, it does look like I have some heteroscedasticity in here, which would be a good thing to use a Garch model for. But for now, we'll just keep going, and we'll take a look at the partial autocorrelation and autocorrelation functions to make sure that I've gotten rid of everything. And yeah, it kind of looks like I did. I still have this really significant. I keep going back. It might be it might be an MA or an AR term that I'm missing right here. It looks like it's probably a seasonal term, right? Because 14 sticks up 2 on both of those. And it's not quite a multiple of 7. That would be 35. So maybe let's try an MA term, because I do have this significant one right here. So we'll try an MA term just because this is about ARIMA models. Okay. So we're sitting here at an AR1, MA1. I have an ARMA model now. Okay. That's still significant. That's very significant as well, not quite as significant. And my constant has become less significant, which is always nice because that means I've definitely picked up some real information. Let's look at our plot now. Still looks about the same. But now I don't have a significant thing over here. I still have this weird seasonality sort of thing. And it looks like, I've got some weird correlations going on. We'll take a look at the information criteria from these two models. Because I've saved them as result 1 and result 2, I can pull those AIC out, and by using this fun little thing, what I can do is I can actually say how much better model 2 is than model 1. And the way to read this is that it's model 2 is this many times better than model 1 in relative terms. So it looks like it's something like 1 trillion times better. Yeah, something like 1 trillion times better. Model 2 is 1 trillion times better than Model 1. So I'm going to keep going with Model 2. Let's add an integrated term because, like I said, it looks pretty stationary just looking at this, right? I'm not super concerned with it being not stationary. But because this is a ARIMA model, let's make it a full ARIMA model with an order 1, 1, 1. This is the model that I used to forecast earlier, just so that you're aware. Now my constant is no longer significant, which is kind of cool. My AR term is still significant, but not nearly as much. But look at how my MA term changed. It's very, very significant now, which is awesome. We can plot the residuals, and not really all that much difference in all actuality between this residual plot and this residual plot. I guess that on average, my residuals are smaller, which is okay. That's cool. Autocorrelation plots looking pretty okay. Let's take a look at how much better Model 3 is from Model 2. 1.04 times 10 to the 20 times better. I'm going to go out on a limb here, and I'm going to say that we should stick with Model 3. Yeah. So let's just do one more thing because my autocorrelation function still seems to tell me that an AR7 model would be a good idea. So let's go ahead and fit that. We fit that, we get this. My MA model is super significant. 7 and 6 are significant. 2 and 1 are also significant. So it's a pretty complicated model at this point, but it is what it is. We'll fit the residuals for this. Still looking more or less the same. Not seeing a whole bunch of differences individually, but now my autocorrelation function and partial autocorrelation function, they're pretty much just noise. Insignificant noise at that. I do have a couple of things that are like spiking out, like at number 14. That's probably because I have some seasonality in my data set and I'm not really doing much with the seasonality in these models. We could always revisit that, but we'll take a look and see how much better this model is. Just really quickly, that's 3, there's my thousands, there's my millions. 857 billion times better Model 4 than Model 3. So let's go ahead and accept that. Because I did have that one that was significant at 14, I decided to try modeling an AR14 model. That took quite a bit of time for my computer to run it, but it run it nonetheless, it did. And when I did that, I got these results. And, you know, I got a couple of significant things out of there, more than I thought that I would. But let's see if my model looks any better. Residuals still looking about the same, guys. Not seeing a whole ton of improvement. They have gotten smaller. But now my autocorrelation function, it's pretty solid, right? Like there's almost no correlation in the residuals. But let's take a look at how much better Model 5 is than Model 4. And we get this result right here. Model 5 is only 16% better than Model 4. So we'll probably stick with Model 4 because it's less complex. And that's pretty much how you would run an AR model. And that's pretty much it. That's all that I wanted to talk to you guys about. I do want to take this opportunity to talk to you guys about I do want to take this opportunity to talk to you guys about something that we are doing here at Barnes Analytics, which is that we are, I don't know why my camera's off. There we go. I wanted to talk to you guys about our summer data science course. It's going to be really cool. I'm really excited about it. It looks like it's going to be way fun, and it should be really, really cool. It's 13 weeks long, and it's really, really cool. We're covering all sorts of topics. We're going to cover one topic every single month, every single week in that 13-week period. And we're going to really take care of you guys and get you up to speed with data science. And by the end of the summer, you will have a really nice portfolio, which you can use to go and search for another job. And it will show a large variety of skills that you have learned over the summer. And what you'll have everything from, this is how you do SQL, right? How you extract data with SQL, to, hey, here's a really fancy vector auto regression model. And then, we'll have things like, graph theory and neural networks. We'll also do a lot of stuff around like just exploring data and doing feature engineering. It should be really fun. I'm looking forward to teaching this class, and I hope to see you in the class. All right, that's all that I've got. Thanks for listening, guys, and have a good one. Bye. Well, actually, before I say bye, let me make sure that there aren't any other questions that have come up in the live stream chat. I'm actually not seeing anything. So